Okay, let's start for today. So, last class, I on Wednesday, I discussed network flows, and I introduced the basically the minimum cost flow problem. So, the goal of today's class will be to sort of continue with that discussion. I want to discuss how would you solve network flow problems using simplex or using LPs, and then we will see a few other things about other models you can formulate using this, some transformations on networks, and I want to also discuss sort of a duality for these problems. Okay, so the goal will be, so this class we will I hope to complete whatever I want to discuss on network flows. There's a chapter in the textbook on network flows. It covers more things on this topic, but for us we will basically I'm just going to focus on some key ideas. Okay, so just a quick recap. Okay, so we were doing this last class. We basically, essentially, network flow problems are LPs on graphs. Okay, so linear programs which are formulated on graphs, and we saw. So this is just a recap. Um, so LPs on graphs. Specifically, we saw two examples last time. One was this what is called shortest path problems, which is finding the shortest way to get from one node to another node, where you have links or the time or the cost it takes to take a particular to traverse a particular link. Okay, so this is one class of problems, and of course there's a natural flow problem here where you're trying to send somebody from one point to another point. But we also saw that there might be problems which don't look like shortest path, but you can formulate it as shortest path. For example, we saw an example which was this problem called dynamic lot sizing, which was not a shortest path problem when you saw it at the start. It was an inventory problem, but with the right sort of formulation, or the right way of thinking about the problem, you can formulate it as a shortest path. Okay, and so the idea is that if you have an efficient algorithm to solve shortest path, then you should be able to solve lot sizing efficiently, because every time you have a specialized algorithm which runs well for a problem, and if you can transform some other problem to that problem, you can use that. Okay, the second class of problems which I introduced was these problems called max flow. Again, we'll come back to this later today. But basically, in these problems, you have not costs on links, but you have capacities on links. And you're trying to send maximum flow from one part or from one node in this graph to some other node in this graph. And again, this can be solved as a network minimum cost network flow problem. Okay. And a third example, which I did not mention, but we have sort of seen before, is this I showed this to you right at the start of the course, are these problems called transportation problems, and we discussed this optimal transport problems, which is even comes up in machine learning. But basically, transportation problems are what? For example, you're just trying you have I mean, let's say you've got links and you've got a graph. You're trying to basically send flow. Let's say you've got a bipartite graph. Okay, you're trying to send flow from one part of the graph to maybe another part of the graph. Okay, so this could be on a bipartite graph. So this is a transportation problem. You have supply nodes, demand nodes. You're trying to send from one part to another part of this graph. Okay, I showed this to you actually in even in week one when I was introducing LPs to you, and it turns out, for example, this is also a network flow problem. There's an underlying graph here from the supply nodes to demand nodes. Uh, an example of this, for example, is this problem called optimal transport, which shows up in machine learning. And if you remember the research seminar which happened a few weeks back, couple of weeks back, I think you guys were there, that is talking about his Wasserstein distances. That's actually an example of this class of problems, basically. Okay, formulated correctly. Okay, okay, where you're trying to transfer one distribution to some other distribution. Okay, you can think of that as a transportation plan. Okay, uh, another variant of this problem is when you have exactly what is called assignment problems. Okay, again, very important class of problems. You have you're trying to assign, let's say, people to jobs. Okay, or tasks. So let's say that people, maybe there's some tasks or jobs. You're trying to assign a person to a task. So there's a supply of one. So each there's one individual each. Maybe there is one job of each type. You have three people and three tasks. And maybe some people can do all the jobs, but maybe some person can only do this job. Okay. So you have a big graph and you're trying to basically allocate people to tasks where you've got a cost of allocating a person I to a job J. Okay. So these type of assignment problems are showing, I mean, a very important class of problems. Um, Anywhere where you're trying to allocate, you're trying to match two sets, you know, I mean, think of a dating profile, maybe a dating app. You're trying to match two people. Any type of matching problem. So that's an assignment type problem. Okay, this is so an assignment problem happens on a bipartite graph. There are generalizations of this on general graphs, which are called matching problems. Okay, so there are many such problems. Okay, matching is on sort of on general graphs. Okay, so there are many sort of problems where you have on networks. And so what I want to do today is I want to sort of talk about network simplex basically. Okay. But there are many versions of matchings, actually matching on general graphs. Maybe you can't naturally formulate it in this class. So let's come back to this later when I do discrete optimization. Okay. Okay. Uh, okay. Any questions? I mean, you guys remember everything from last class? We can proceed. Okay. Okay. So one thing I want to mention is that sometimes problems, so there are useful transformations to know sometimes, which is you try to transform a problem into a network optimization, a network flow problem. So sometimes there are problems where you want to make some transformation to the network so that it satisfies some condition, and there's some of these properties transformations are useful. So I'll just show you I mean 2 to 4 transformations. So for example, okay, I can take a network. Maybe I've got multiple um, uh, sorry, yeah, so if I've got multiple, let's say, source and sink nodes, okay, you can actually always transform this problem to a single source and a single sink node, okay, with some appropriate transformation. Okay. So let's say I've got a network. Okay. Maybe let's say there are 3 supply points. Okay. So maybe there's a 10 units coming here, maybe 2 here, maybe 4 here, maybe let's say 9 and 7. Okay. So I've got 16 units of flow external into this graph in these 3 nodes, and maybe 16 coming out. And I've got a network of some structure. Okay. Okay. So there are multiple sources. There are 3 sources here, 3 sources and 2 sinks. Okay. So I claim that you can always transform such a problem to a single source and a single sink node. Okay. So you have to add something. I mean, you have to modify the network a little bit. Okay. So how would we do this? Okay. So let's take this network. Okay. So I take this original network, and all I do is I basically I make some slight modifications to this network. Okay. So for example, I add 2 new nodes to this. Let's call this a node T. I'm adding 2 new nodes to this. I'm sorry. I'm adding 2 new edges to this graph and 1 new node, and I basically make the flow on this edge to be 16. Okay, so 9 plus 7, 16, and I make the capacity of this. So I make the uij on this link, to be 9 and uij to be 7. Okay, so if I have to send in 16 links here and my capacities are 9 and 7, there's only one way to do it. Upper bounds are 9 and 7. I have to send 9 on this and 7 on this. Okay, so I can do the same thing on the source side. Okay, so I could have added a source node. I just added links here. send in an external flow of 10 plus 4, 14 plus 2, 16, and make the capacities here to be 4, I guess 10 and 2. Okay. So this is one source, one sink. Everything else now is a transshipment node, except for the. Okay. So solving this problem is equivalent to solving a network flow problem on this graph. Okay. So if I was to have a method which can solve it on this single source, single sink, I can do it for a multiple source, multiple sink. Is that clear? These are upper bound capacities. Okay. There's only one way to send this. Okay. So some other transformations which are useful. Okay. So remember in my network flow problem, there are two things. Okay. If you remember the problem, I've got capacities on arcs. I'm sorry, I've got costs on arcs and capacities on arcs. Okay. Sometimes you might have capacities on nodes. Okay. So remember, everything in my network flow problem, my flow is on an edge, on a link, xij. Okay. So suppose I've got a graph where there is some inflow, there is some outflow, but maybe I've got a constraint that says that let's say at most let's say 5 units I have to flow through node I. Okay. So one way I could do is, of course, I could say that the total amount of flow coming in here is that I sum up all these inflows and say that they are less than or equal to 5. An alternate way to do this, where if you want to preserve just the same, I mean, that will have some additional constraints saying that the total sum of inflows is at most 5. A second way we could do this, where we keep sort of a network structure where everything is on, you have only flow conservation and capacity constraints on edges, is to simply duplicate the node. Okay. So you basically create two nodes I, and let's call this I dash. Okay, there's a new node. I create a link between I and I dash. Sorry, let me make this a bit bigger so it's clear. I dash. There's a link going from I to I dash. Incoming into I, income into I, outgoing out of I, outgo out of I dash. Okay. And what do I do? I simply say that the capacity of this link, the upper bound on this I dash, is 5. If exactly 5 units have to flow here, at most 5 units can flow here, this will force this capacity, the flow here, to be at most 5. Okay. So the only reason I'm doing this is this will preserve the network flow structure. That means there is only flow conservation at nodes and capacities on links. Okay. Otherwise, you have to put in additional constraints saying that sums of flows into an edge, into a node, is above something or below something, which is a slightly different type of constraint to what we saw. We saw only two types of constraints in network flows: flow conservation, capacity constraints on links. Okay. Okay. Is that clear? Any questions there? Okay. So this can be useful. You can again transform. We saw another transformation here. A third transformation is multiple edges between nodes. Again, this is easy to deal with actually. Okay. So suppose I got, for some reason, let's say I've got two nodes and maybe I've got multiple links joining this. Okay. So I told you that when we think about network flow problems, I will only allow one link between I and J. Okay. For some, let's say I've got multiple ways to get from I to J. Okay. Multiple arcs. Okay. You can transform this to a standard network flow problem. You can simply index these things differently with different indices for the arcs. Another way you can think about this is simply add in some sort of extra nodes here. And you will get back a single These are again transshipment nodes. Again, you will have single links between edges and between two pairs of nodes. These two networks are the same. Any capacity here can be made a capacity here. Okay, and this is a transshipment node. So nothing, there'll be no external flow here. So this will be transshipment. Okay, so there's no, dealing with multiple edges is not particularly hard. Okay, between nodes. Okay, any questions? You might, okay. So why might you have, okay, you might be able to merge it. Why might you have multiple links? Because the costs on these links could be different. Or there might be different capacities on these links, for example. So you might have like, maybe you can send 5 units of flow here, maybe 10 units of flow here, but the capacities are different and so on. Okay. So you might, if you've got multiple ways to send flow, okay. So maybe you want to send, I don't know, 20 units here. Maybe the capacity here is 10. Maybe the capacity here is 7. Maybe the capacity here is, I don't know, 15. And you've got different costs. So you've got to figure out which ones to use. Okay. Okay. Now, the next one, which is I mean, this idea of merging that you're talking about is if you have piecewise linear convex costs on links. Okay. So remember what we know from linear programming, right? I know LPs I can solve, but I know I can formulate piecewise linear convex LPs also as LPs. We have seen these tricks in our initial couple of weeks of classes. There are natural tricks using this sort of epigraph formulation. You just introduce this new variable, you bring it in, and you can basically transform piecewise linear convex LPs to LPs. We have seen this. So you should expect piecewise linear convex cost network flow problems should also be transferable to network flow problems. Okay. So what does this mean? This means that suppose I've got an edge, okay, I and j, and my cost. So right now my costs are what? Cij times xij, right? This is my linear cost. But let's think of a variant of this problem where maybe when I send flow on this link, it is not a linear function, but it's piecewise linear convex. So this is piecewise linear convex cost. Okay. So I claim that this you can also formulate as a network, as a standard linear cost network flow problem. Okay. So you can transform it like how you can take piecewise linear convex LP and make it an LP. You can take piecewise linear convex cost network flows and make it a network flow problem. Okay. Why? So we have to think about what this cost looks like. So let's take an example. Let's say this is xij. Let's say this is the cost function Cij xij. Okay. And let's say my cost is initially, let's say, increases at some rate. Then maybe it increases at a slightly different rate. And then maybe then it increases at some other rate. Okay. So that's a piecewise linear convex cost function, right? Okay. So each of these pieces will have, what? There's an intercept. I'm sorry, there's a breakpoint and there's a slope. Okay. So let's just put in some numbers here. Okay. So let's say the slope here is alpha 1. Let's say the slope here is alpha 2. Let's say the slope here is alpha 3. Okay. And let's say that this is, let's say 0. Let's say this is beta 1, beta 2, and maybe this goes off to infinity. Okay. Okay. Now this is clearly not a linear function. And in this, it's clear that alpha 3 is greater than alpha 2 is greater than alpha 1. I mean, that's what it means to be a convex function. In a convex function, the slopes have to be increasing, right? As you move down, as you move in this direction. Okay. Okay. So what would you do in this case? How would you formulate this as a network flow problem? So the idea is as many pieces as you have in your cost function, create as many links as that. Okay. So here's a transformation. Take I and j. We've got 3 pieces in this cost. So let's create 3 arcs. between I and j. Okay. Okay. So there might be some incoming arcs, there might be outgoing arcs. That's fine. Let's look at this part. Okay. So what do I want? So on this, I'm going to let, so let's say the first arc. I want this to capture the flow if it is between 0 and beta 1. So I'm going to make the capacity of this 0 up to beta 1. So I can only send between 0 and beta 1. So this is my capacity, upper and lower bounds of this link. Okay. Okay. If I send flow on this link, since my slope is alpha 1, I want the cost on this link to be alpha 1, the cost, the unit cost. Okay. So for example, if I send, let's say, beta 1 by 2 units on this link, it will be alpha 1 times beta 1 by 2. So this is a unit cost. So this is a linear cost function. So as long as I'm sending between 0 and beta 1, I want to use this link. Okay. Now, if I'm trying to send flow here, on this next link, I'm going to let my flow be between 0 and beta 2 minus beta 1, which means that up to beta 1, I'm going to use this link. If my inflow is more than beta 1, I want to use this link initially, get this cost, and then the remaining surplus, which I cannot send on this link because of the capacity, I will send it on this link. That can go up to beta 2 minus beta 1, which means that the total sum of the flow across these two links can be at most beta 2, which is up to this part. Okay. And what do I want for the cost of this? I want the cost of this to increase at the rate of alpha 2. And on this last link, I want it to be alpha 3, 0 up to infinity. Okay. So what is minimum cost flow going to do? A min cost flow problem will first saturate a min cost flow problem. So this alpha is the cost. Okay. And these are capacities. Okay. So what will min cost do? It will first saturate this, then saturate this, then saturate this. By doing this, I will pick up the corresponding cost functions because up to this, I will get this rate. When I use these two, I will basically pick up this part of the graph. And beyond this, I'll pick up this part of the graph. So if you just check, you'll find that you will pick up this piecewise linear convex cost. But this is just parallel arcs. And this is just, we've already seen parallel arcs can be transformed. So this becomes again a minimum cost flow problem. So this is useful, okay? So you can take, for some reason you don't like linear functions, you want to work with nonlinear functions. In principle, you could discretize too. You could take a discretization of a nonlinear convex cost function, do a discretization of it, and approximate it using this technique. Okay. Okay. So this is again useful because sometimes cost functions, you will see in certain problems, things will not grow linearly, but they will have an increasing rate of the slopes will increase basically as your flow increases. Okay. Okay. And there are many such other transformations. Okay. I'm not going to do it here, but you can actually note there's actually a book by Orlins, Jim Orlins, Tom McNanty, who used to actually be a president at SUTD. He was the first president of the university. So both of these are MIT profs. And Ahuja, it's called Network Flows. It's a full 700-page book on network flows, okay, and network optimization. So you can, like I said, you can do a full graduate class just on this topic if you wanted to, okay. So if you want to see other transformations or sometime later in your research you're interested in these type of things, you can go back and look at this book, okay. But these are useful ones to know. Okay, good. Any questions before I proceed? I'm going to now go to network simplex, but I just want to know if there are any questions about this parts. So the idea is these transformations are just useful to know. You can take a problem and maybe transform it back to a network flow problem and then apply the techniques for networks flows. Okay. Okay. So what we are going to do next is we are going to now go back and look at min cost network flow that we discussed last time and network simplex. Okay. Okay. So we're now going to study the structure of the problem and think about how simplex will look like for this problem. Okay. Now there's a couple of other things about network flow problems which are very useful. That is, we will see that we are solving linear programs, but we will actually get integer solutions if our data is integer. Okay, which is a very important property of network flow problems. So we'll discuss those issues now. Okay. Okay. So let me just remind you what the problem is. Okay. So remember, a network flow problem, a general problem is this. So you're given a directed graph. Okay. You've got capacities, you've got costs on links. Okay. These are the costs. Okay. And for now, for at this point, I'm going to focus on the uncapacitated problem, which is Li, the lower bounds on the arc flows are 0, and UIG are the upper bounds are infinity for every ij in E. Okay. So this is an uncapacitated network flow. There's a lower bound of 0, but the upper bound is infinity. Okay. If the upper bound is positive, you can still you can basically modify this. The algorithm will look at, okay, with it's not too difficult to modify it. The textbook has it, but this will help us. No, we can stay within the standard form LPs to discuss this problem. Okay. Okay. So how would the problem look like? So in if I write it explicitly, the minimum cost network flow problem is okay. And of course, I've got supplies and demands for nodes. Okay. Okay. So the problem is I want to minimize. So I'm just going to write it first one time explicitly, and then we'll use matrix notations. So you got outflow out of node J, out of node I. So take all the edges going out of node I, subtract away all the edges coming into node I. Okay. This is from last time, is equal to Bi for every node in this graph. And right now, because I'm assuming lower bounds are 0 and upper bounds are infinity, Xij is non-negative for every ij in E. Okay. So this is flow conservation. This is capacity, but these are just lower bound capacity constraints. Okay. So remember flow conservation, you got a node I, there's an inflow of Bi. If it's positive, it's a supply. If it is negative, it's demand. So if there's minus 5 units coming in, it means there are 5 units going out. Okay. If the if it's 0, it's transshipment. You've got incoming links, you've got outgoing links. So total outflow minus total inflow is equal to this. Or another way to say this is the total amount of arc flow into this node, external and internal, if you take this side, is a total going out. Okay, so this total sum of all these flows has to be equal to this flow. Okay, so it's getting cold. Let's put a jacket on. Okay. Okay, is that clear? The formulation? Okay, so let's now think about this in matrix form. Okay, so in matrix form, it's what? Minimum C transpose X subject to, this is linear constraints. So AX equal to B, X non-negative. Okay, so this is exactly standard form. Okay, LP. Now that is but only thing is the A here has got some structure. It's not when you do linear programs, A can be arbitrary. It can be any matrix basically of numbers. But here A has a structure because if you look at the coefficients, it's either going to be 1 or a -1, or if there's no edge on a graph, I'm sorry, if a particular edge doesn't affect doesn't go into this node or come out of this node, there should be 0. So the entries of this matrix A will only have -1, 1, or 0. So it's a structured matrix. Okay. So this matrix, so A is what is called a node arc incidence matrix. It's a way to store the structure of a directed graph. Okay, it's so this matrix A has some structure. Okay, so let's look at what this matrix looks like. Okay, so let me just tell you the definition. If you think about what this, so what is the size of this matrix? Okay, okay, okay. So now there's okay. So if n is the number of nodes and m is the number of edges, okay, this matrix A, the number of rows here is the number of nodes, and the number of columns is how many ever edges are there in my graph. So this A is a matrix of size n by m. Okay, so we're using n here because for nodes. Okay, so this exactly, I mean, this is sort of opposite to what we did in LPs. In LPs, my A was n was my number of variables, and m was the number of equality constraints. Because you're talking about nodes here, so I'm using n for number of nodes, and m is the number of edges. My flows, my variables are on edges basically, right? My variables are flows on edges. Okay, so in this problem, actually, I've got m variables and n equality constraints. Okay, but it's fine. We don't have to get stuck up with n and m. You know, these are just numbers, right? These are just variables, right? Okay, so A is of size n by m. Okay, okay, is that clear? Okay, I'm using n for number of nodes. That's why n nodes. Okay, okay. So let's look at what the structure of A is. So what is the definition of A? So A is a matrix of size n by n. So A, let me call this AIK. Okay. Now you have to be a bit careful here because our variables are xij. Okay. So every arc has two, there are two indices which define a variable. Okay. So it's actually some, so I'll first define AIK. So AIK is what? If a edge, I'm sorry, if you look at this, sorry, I went all the way up there. Okay. If you look at this, if an edge leaves a node, it gets 1. If an edge enters a node, it gets -1. If an edge is not connected to a node, it gets 0 in that row, right? So at node I, all this will have +1, all this will have -1, all these will have 0. Okay. So what is AIK? It's +1 if uh, if k if I is the start node of edge k. So this is a start node. Okay. So if this is edge k, okay, I is the start node, -1 if I is the end node of edge k, and 0 otherwise. Okay. So k is in principle a two, I mean, the way we index edges are with two variables, right? I and j, right? IJ. But when I'm talking about matrix, it's column number basically, right? So k is a column number basically in some ways. Okay. Okay. So let's do an example. It'll be clear. It's not particularly complicated. Okay. So let's take an example. So let's take a particular graph. Okay. So how will A look like? Okay. So A is a matrix. There are 4 nodes. 1, 2, 3, 4. Okay, there's going to be a row for each node. Coming out of node 1 are 2 links, 1, 2, and 1, 3. Okay. So if my first link is 1, 2, and my first column is 1, 3, essentially 1, 2 will be, it's leaving 1, going into 2. 1, 3 is leaving 1, going into 3. Okay. 1, 2 does not involve 3 and 4. 1, 3 does not involve 2 and 4. Node 2. Okay. At node 2, so I've done 1, 2, I've done 1, 3. So this is my first link. So 2, 3 is what? 2, 3 will exit 2, enter 3. So this is 2, 3. Link column corresponding to 2, 3. Then 2, 4 will be 0, 1, 0, minus 1. That's 2, 4. Then got 3, 4. 1, 2, 3, 4, 5. Yeah, so the last will be 3, 4. Link 3, 4 will be 0, 0, 1, minus 1. Okay, so this is a 4 by 5 matrix, 4 rows for 4 nodes, 5 columns for 5 edges. Okay, is that clear?
And can we switch the edges with columns?
You could have written 1, 2 later. Yeah, that's fine. You can. I mean, you can. The order is not important here, right? I could permute, but I mean, it could be that 1, 2 could have been here, but the edge which what is important is the edge which corresponds. If 1, 2 was the last column, that's perfectly fine. But you have to ensure that that column will have a 1 for the node 1 and a minus 1 for node 1, for node 2. Does it make sense or no? So just to make this clear, you could have also written A as, so what he's saying is, could I have written it in this form? Let's say I move these 4 at the start, and the last one I write is 1, minus 1, 0, 1. That's perfectly fine.
0, 0.
Sorry, 0, 0. Sorry, and 0. You're right. Okay, and this reminds me of I mean, this already is there's a point here. Every column here can have exactly 1, 1, and 1 minus 1. Okay, because an edge involves only 2 nodes, one incoming, one outgoing. Okay, so this is perfectly fine. Okay, it's just a reordering of columns. Okay, as long as you know that this corresponds, I mean, it's clear that this corresponds to link 1, 2 in the graph. Okay. 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 Now, so a couple of notes here. So note 1. Okay. Exactly 1 plus 1 and 1 minus 1 in each column. Okay. This has to be the case in the incidence matrix. Okay. This is not true for general LPs, but this comes because of the network structure. Okay. And all other entries are 0. Okay. So it'll be a relatively sparse graph in general. Okay. If n times n into m, so there'll be quite a few zeros in this graph, basically. Okay. 2, and this is sort of different. I mean, okay, this is a property which is true in this for this incidence matrix is this matrix actually is not linearly, the rows of this matrix are not linearly independent. Okay. So there is a dependence in these rows. Okay. Why is this the case? Okay. Let's take the vector of all ones and multiply it with A. Okay. So this is like, I'm going to call this E transpose. So let's take, I take a vector of all ones. So as many as a number of nodes and pre-multiply that with 1. I'm sorry, with A. Okay. So suppose you take 1, 1, 1, 1 and pre-multiply this with A. What will happen? It'll be 1 times 1 minus 1 times 1, which will give you 0. Second column, 1 minus 1, 0. 1 minus 1, 0. So this will give you a vector of all zeros, which means that there's linear dependence because you can take a row of A and write it as a linear combination of the other rows. Okay. So that is the rows of A are linearly dependent. Okay. Another way you can think about this is if I tell you that there are, I mean, just as a, just intuitively, if I tell you that there are 5 units coming in here, okay, and then let's say that 2 units, I mean, let's say I've got flow conservation here, in these 3 nodes, the flow in the last node actually is implied from the other nodes, basically. You cannot, there's no degree of freedom there. Okay. So if I send 3 units here, 2 units here, let's say there's 0, 5 units have to come out here. There's no other way for the flow, for this network is balanced, basically. Okay. So it basically means that somehow flow conservation on 3 nodes are linearly independent, but the last one is implied by the remaining. It's a closed network, right? Okay. Okay. So there's linear dependence in this. So whenever we do, if you remember LPs, we require basis matrix. Our basis matrix has to be linearly independent rows, basically. Okay. So we're going to drop one row. So it turns out you can actually drop a row. Okay. So we can, so we will define, okay, so we will define, we will use for the, this is only for the development of the simplex method. Okay. So we will use a truncated matrix. I'm going to call this A tilde of size n minus 1 into m. Okay. Where we drop one row of A. Okay. Okay. So let's take this example. Let me just take this back. Okay, so let's go back to this example. Okay. Let's say I drop a particular row, and I could have chosen to drop any row actually. Let's say I'm going to drop this last row. Okay. So this is going to be A tilde. It's going to be a matrix of only size 3 by 5. Okay. Now I claim that this matrix is linearly independent. Okay. So this is a matrix of size 3 by 5, right? Okay. So if it's a full rank, which means the rows are linearly independent, I should have 3 linearly independent vectors I can find in this. Okay. So for example, if you look at this matrix, if you look at the columns, let's say you look at, so remember row rank and column rank is the same. Okay. So if you look at if you look at if you look at, for example, this column, so I'm going to drop this. So take this 0, 0, 1. That's one vector. Take 0, 1, 0. This one. And let's take, 1, 0, minus 1. These 3 are linearly independent. Okay. It should be quite clear. These 2 are 2 degrees and the third one comes from this. Okay. So these are linearly independent. Okay. So we're going to always do, what we're going to do is we're going to work with a truncated matrix where we're going to drop truncated matrix where we're going to drop one row basically. Okay. Okay. Now when we do this, of course we'll have to modify the LP because we drop one constraint, which is not basically is redundant, that constraint. Okay. So what we're going to do is, okay, so we're going to okay, so let's just set up the standard form LP. Okay, so here is the, so our network simplex. So okay, so we are going to take minimum C transpose X subject to AX equal to B, X non-negative, and you can transform this to minimum C transpose X subject to A tilde X equal to B tilde, X non-negative. What is B tilde? I drop the corresponding entry of B basically. I dropped a row, right? So that corresponds to a particular entry in B, the corresponding row in B. I have to drop that. Okay. I have one lesser constraint. So if this was n into m equality, I'm sorry, this is a n, there were n equalities here. There are n minus 1 equalities here. Okay. So you can develop simplex on this basically. Okay. Okay. Good. Any questions? Okay. So a couple of things okay. So before we, okay. So the key is going to be, what does a basis mean for this problem? What is a basic feasible solution? Okay. So you're going to make a couple of assumptions for network for it. Okay. For the problem to be sort of interesting. So assumptions, 2 assumptions. One is we have to assume that the total, I mean, basically it has to be balanced. The total supply has to be equal to total demand. Okay. So if you have a network flow problem, if I've got 20 units of flow external, there should be 20 units of demand. Okay. So this is sort of, without this, the problem will not be feasible. Okay. No, if I'm sending in 20 units and just exiting 10 units, what happens to the remaining 10 units? Okay. So this is almost a necessity for it to be feasible. Okay. So this is to ensure it's total supply equal to total demand. So this is natural. Otherwise, the problem is not well formulated. Okay. And the second is the underlying uh, so underlying uh, undirected graph in G, V, comma, E is connected. Okay. So what this means is, if you've got a problem, again, this is not a particularly complicated thing, but imagine you've got a problem like this. Okay, you're solving some network flow problem like this. This is not connected, right? There is one part of the graph here and one part of the graph here. But then I would just solve the problem separately because I cannot send flow on this from to this part. Okay, again, this is a lot of generality. I would just decompose it into two sub problems, and I would solve it on this separately and this separately. So again, these two assumptions are almost like natural to think about when you develop the algorithm. Okay, else just solve smaller sub problems. Okay, okay. So these are sort of I think are relatively natural. Okay, so with this, let's think about network simplex. Okay, okay. Any questions before we move on? Okay. Okay. Now the key thing we require is, what does it mean for a basic feasible solution for these problems? And it turns out the key graph structure you require are trees. Okay. So you remember I discussed trees last class when we discussed what a tree in a graph is. So it turns out that what we are going to require is the notion of what is called a tree solution. Okay. So I'm going to tell you what a tree solution is. Okay. And so my goal is to give you key ideas of network simplex. We won't work through an example here. The book has examples. You can work through it on your own. But I want to give you key ideas which I think are useful to know. Okay. Okay. So what's a tree solution? Okay. So we're going to define what does it mean for a flow to be a tree solution. And we will see that this is like what basic feasible solutions are. Okay. So a flow X is a tree solution. Okay. If, so I'm giving a definition here. If it can be constructed as follows. Okay. So a couple of steps. So one, first pick a set T, which is a subset of E, okay, of n minus 1 edges. Okay. So remember, I've got a graph V comma E. The number of nodes in my graph is n. This graph is connected. Okay. That means the underlying graph is connected. The undirected graph is connected. Okay. If I want a tree, okay, by the way, a tree is an undirected structure. Okay. If I require a tree on n nodes, how many edges does it have to have? We discussed this last class. If I've got 5 nodes, if I have a tree on this graph, how many edges should it have? 4. So you require n minus 1 edges. Pick a set T of n minus 1 edges that forms a spanning tree. Spanning tree of the underlying graph. Okay. Okay, that's a tree. Okay, so set of edges. What do I do? Set flows xij to be 0 for every edge which is not in the tree. Okay. What does this look like when you compare it to LPs, standard LPs? This is a notion of non-basic variables. What do we do in standard form LPs? Non-basic variables, set it to 0, find the basic variables. Set all the flows on the arcs which are not on the tree, make them 0. Now what do we do? Use flow conservation to find flows on the edges, uh, to find flows xij on edges ij in T. Okay. And I will show you how to do this. Okay. There's basically going to be a unique way to do this for a tree. Okay. We will see this. Okay. It turns out when we do this, because a tree is, remember, an undirected structure. Okay. We forget directions. Okay. I will show you how to do this. If all these flows xij are non-negative when we do this, then it is a feasible tree solution. Okay. Which is going to be what is a basic feasible solution. When you do only this first three steps, it's a basic solution, but feasibility may not be guaranteed because your flows may not be non-negative. Then it becomes a feasible tree solution. Okay. So I'll show you an example. We'll do a couple of examples just to illustrate this idea. And see this. Okay. Is that clear what you're doing there? Okay. Okay. So let's do an example. So let's take the same network. And I'm just going to put in some flows now to just make this. I'm just going to add in some flows here to make this problem, to illustrate what we're trying to do. Okay. So let's say there's a flow of 2 incoming, 3 incoming, 1 outgoing, and 4 outgoing. Okay. So that's 2 plus 3, 5, 1 plus 4, 5. That's a balanced graph. Okay. It's a connected graph. So I can think about spanning trees on this graph. Okay. So let's take one spanning tree. Let's take the first spanning tree. Let's take the spanning tree 1, 2, let's say 4 and 3. Let's take this spanning tree. Okay. If I just, I've got, so remember n is 3 and n is 4 in this graph. A spanning tree will have 3 edges and it will not have a cycle and it's connected, right? So that's a spanning tree. If you forget the directions. Okay. My flow here is 2. My flow here is 3. Flow here is 4. And flow here is 1. Okay. So if there's a outflow of 4 here, 4 has to flow on this link. There is 4 flowing here, 3 coming here. So there should be 1 incoming here, 1 plus 3 to give 4. I'm going from the leaf node towards I'm working from the leaf nodes. At the leaf node, there's only one link, right? So I can find out things about the leaf node quickly. So I'm always working from the leaf node backwards. Okay. So 4, this gives me 4. So 3 plus 1, 4. 2 coming in, 1 going out. So this should be 1. That balances with 1. This should balance out because, you don't require to do flow conservation at all nodes. It's a balanced graph. Okay. So what is this saying? This flow is 1. This flow is 4. This flow is 1. This flow is 1. Every other link which is not shown in this graph has a flow of 0. Right? This is a feasible tree solution. Why? The flow are only on the edges of a tree and everything is non-negative. Let's take a different tree. Okay, and there are other trees you can create in this graph. Let's take the following tree. Let's take maybe 1, 2, maybe 3, maybe 4. Okay. What do you have? You have 2 units coming in here, 3 units coming in here, 1 unit here, and 4 units out here. Okay. Let's try to do the same thing. Start from the leaf nodes, use flow conservation to find the flows on the links. Okay, 4 units coming in here, 4 units has to flow here. Okay. 1 unit going out, 4 units going out. So 5 units has to flow in this direction. 5 units flowing here, 2 units flowing here. You can see what's going to happen here. 5 units coming out, but there's only 2 units inflow. So how are you going to balance this? Essentially, there should be -3 flowing out in this direction. But the direction actually is, flow should be in this way. So this is -3, -3 and 3 balance out, it gives me 0. This is not a feasible tree solution because this tree is giving me a flow of -3 on this link, which my flows have to be non-negative. So this is not a feasible tree solution. So some trees will give me feasible values. Tree solution, some trees will not give me feasible values. Okay. So this is like a basic feasible solution. This is a basic solution, but not feasible. Exactly like what we've done in LP is concretized to this example. Okay. The only thing is for flow conservation, you just have to go from work from the leaves inwards towards the root node. Okay, work from the leaf nodes towards the center of the graph. Okay. Okay. Is that clear? Okay. So what we are going to show next is that this whenever you find a tree solution, I mean, so essentially what we're going to say is a tree solution will always give you a unique solution. So it's like a concept of a basic solution. We will try to show that next. And then we'll argue that these solutions will always be integral. Observe that my input here was integers and my flows here were integers. So it's going to always be the case that you're going to get integer values if your inputs are integers. So we'll come back and sort of argue this formally. Okay. After the break, we'll do this. It's 11 o'clock. We'll start in about 5 minutes. Okay. Okay, let's start. Yeah. Um, okay. So, so we need. So I want to just talk about why the. Okay. So some properties about this basis matrix, which is going to be relevant for us. So I want to just quickly remind you a couple of things about determinants, which will be important for this part. So just a bit of refresher, basically, for you from your linear algebra. So one is, so we're going to use some property over determinants. So remember what a determinant is. If I've got a matrix of, let's say, size 2 by 2, it's A11, A22 minus A21, A212. Okay. If I take a determinant of size 3 by 3, of a matrix size 3 by 3, what you're going to do is you're going to calculate this determinant along every entry. So you take one row, you take, if you remember the definition of a determinant, you take A11, you find the determinant of the smaller submatrix, 2 by 2 matrix. Okay. So A22, A23, A32, A33. You do this for, take A11, compute this, what's called the cofactor. You do this, then you repeat this for the next one, A12, determinant of A23, A33, A21, A31 plus A13, determinant A21. So you have to do this. So you'll get n such terms if it's an n by n matrix. Okay, and then you're going to use essentially smaller. You're going to use smaller submatrices and then do this recursively. Okay. Sorry. Yeah. So I do it. It's minus A12 if I use it in this order. So I've changed the order here. A23 and A33, I've written it this way. You're right. What you're saying is right. It's minus A12 if I write it in the order A21, A31, A23. Yeah. So what she's saying is, okay, so let me write it the way let me write it in the way you want. If you change yeah. So if you write it in that way, it'll be A. Both are equivalent. Yeah. A21, A31, A A23, A33. Okay. Okay. Fine. Now more generally, okay, you can compute the determinant of a matrix A, okay, by taking summation J from of size n by n, okay, taking the the first row, the jth column, okay, times this what is called the cofactor. You basically have to do -1. This is the formula that you're mentioning, I plus j. Sorry, -1. In this case, it will be. So let me write down the formula Cij, this C1j, where this thing is this cofactor that we just wrote down here, C1j, where Cij is given by -1 to the power I plus j, determinant of this matrix Aij bar. Okay. So drop row I and column j. Okay. And you're going to repeat this basically. Okay. So find for a smaller matrix, you have to repeat it and so on. Okay. Okay. So again, this is all from your earlier, from your maybe your undergraduate classes. Okay. So just two things that we require. Okay. One is this Kramer's rule. Okay. Or Kramer's theorem. Okay. So what does it say? If the determinant of A is non-zero, if determinant of A is non-zero, okay, and I'm trying to solve Ax equal to B, okay, solution of Ax equal to B is given by what? Xj is the determinant of a matrix, let's call this Aj bar, over the determinant of A. But what do you do in Aj bar? You replace the jth column of A by B. Okay, this is Kramer's rule. Okay, it says that if you're trying to solve Ax equal to B, so this is, of course, A is a square matrix, okay, and it is non-singular. So it's non-singular basically, it's invertible, okay. Then the jth component of this vector is given by the determinant of this matrix, where you say take the columns of A, replace the jth column of A by this vector B, divide by determinant of A. Okay. So what is key here is the determinant of A shows up in sort of the denominator of this expression. Okay. Okay. So we're going to use this property. More generally, you can write actually A inverse as 1 by the determinant of A times all these cofactors that you find, C11, C21 up to Cn1. Okay. Okay. So I think the most important thing, the details of these cofactors are not important for this course. Okay. What is important is the fact that this determinant of A shows up in the denominator, and it is what you're going to divide by. Okay. This is the most important thing that I want you to take account of. That is, the inverse has this determinant of A in the denominator, and the solution of a set of linear equations has determinant A showing in the denominator. So if this number is well behaved, you're going to get integer solutions. Okay, that's what we're going to look at. Okay, this is not the way you typically solve linear equations, but it's a formula which is useful to know. Okay. Okay. You might or might not have seen this. If you've not seen it, that's fine. Maybe just go back and look at some linear algebra notes. But for me, what is most relevant is the fact that the determinant of A shows up in the denominator of these formulas when you calculate the solutions of linear equations. Okay. The exact formula is not critical for this course. Okay. Okay. So the first, okay, and of course, if a matrix is, I should also mention this about determinants, is if a matrix is diagonal, the determinant is just the product of the diagonal entries. Okay. So if A is diagonal, the only diagonal entries, the determinant is the product of diagonals. Okay. So maybe I should mention that if A is a diagonal matrix, the determinant is just the product of the diagonals. Okay. Okay. Fine. So let's first come to, so let's do the first so let me make the first claim. Okay. So basically, given a spanning tree, so what we just saw when we solved those equations in the example, I showed you a tree and I showed you there's a unique solution. Okay. So given a spanning tree, T, okay, the system of equations xij equal to 0 for every edge not in the tree and flow conservation. And flow conservation comes is what? A tilde x equal to B tilde. That's flow conservation as a unique solution. Okay. So what are we trying to say in this theorem? I'm trying to say that what we saw here, we solved this equation. No, when I gave you a tree and I solved for it, I found a unique solution. There's only one way to find the solution to this problem. I gave you a different tree, there's a unique solution to this problem. Okay. So we're just going to concretize that with a result, with a theorem. Okay. Why is this the case? Okay. Essentially, we are taking a submatrix of, so when we are solving for this, so when xij is 0, okay, so what is it doing? It's basically forcing some of these variables to be 0. Okay. So we are left with, so we are solving bx equal to, so b, some basic variables equal to b tilde, where b uh, is what? B is a n minus 1 into n minus 1 matrix formed using the columns of A tilde, using the columns of A tilde corresponding to the edges ij in T. Okay, so what are we doing when we are forcing all the non-basic variables to be 0? What we think of non-basic variables, we are left with basically a set of columns that we are using because each x variable corresponds to a column of this A matrix. So we are only taking some of the columns. The columns correspond to the edges of the tree. There are basically n minus one of them. So we're taking those columns basically, and you're solving for bx equal to b tilde, and this b is basically the basic variables. Okay, maybe I should call this xt because the tree. So let's call this t. Okay. Okay. Now the key idea is so we want to argue what is b is non-singular. Okay. So you can do this. You can see this by basically doing a renumbering of the graph. Okay. So to show b is non-singular, okay, we renumber the nodes in the graph. Okay. By increasing node numbers from the leaf inwards. Okay. So leaf nodes will have small numbers and we're going to keep increasing the node numbers up. So we're basically reordering the columns and the rows, okay, from leaf inwards. And after you do this and reorder columns and renumber edges for I comma j using minimum of I comma j. Okay, so I'll show you what this does. Essentially, this makes B, we will see this makes B a lower triangular matrix with non-zeros along the diagonal. Okay. And therefore, B is non-singular basically. Because the determinant of this thing will be, it's got non-zero entries along the diagonal and it's lower triangular. Okay, so if you calculate the determinant of this, it will be non-zero. Okay, so maybe let's do an example. I'll show you the numbering just to show you how this works. Let's take this same graph, 1, 2, 3, 4. So remember you have this graph 1, 2, 3, 4. Okay. Okay. So let's say I take a particular tree. Okay, let's take this tree. 1. Okay. So what I'm going to do is I'm going to renumber these nodes going. I'm just going to renumber this group, the nodes of this graph. Okay, so this is a tree. I'm going to renumber it so that it is the leaf nodes are small numbered. So let's call this 1. Okay. So you can increase this going inward. So let's call this maybe 2, 3, 4. I'm just renumbering. Okay. And then I'm going to assign a node edge number to be the minimum of the two nodes connecting that the edge is connecting to. So minimum of 1 and 3 is 1. Minimum of 3 and 4 is 3. Minimum of 2 and 4 is 2. So all this does is it reorders the matrix. Okay. So if you look at your matrix, this matrix B, okay. Okay. So the edge 1 links 1 and it should be incoming to 1, outgoing out of 3. This is the first edge. 2, 2, 4 is what? 0, -1, 0, and 4 is the last node, but we have dropped the last edge. We have dropped the n-1th node basically. Okay. And what is the last one? Edge 3, 4 will be 0, 0, -1. This is a diagonal lower triangular matrix where there are only non-zeros along the diagonal. In this example, it's all -1 and there's a +1 here. This matrix will always have determinant non-zero. Okay. So any matrix which is lower triangular where determinants are non-zero will have, where the diagonal entries are non-zero will have determinant non-zero. Okay, which means B is invertible, which means you have a unique solution to this set of equations, which is what we saw in the example, but this is just the formal argument for it. Okay. Okay. Is that clear? You can try this for other trees. I will let you try on your own. Okay, just to check the numbering works. Okay. So the key idea is that note basic feasible solution is exactly equivalent to a feasible tree solution. Okay. Now we will just look at what it means for how does network simplex look like. Okay. So let me just take the minimum cost flow problem. Okay, so this is my minimum cost flow problem. Okay. Remember this problem, and actually we have not looked at it so far. This problem has a dual. Okay. So this is the primal. What's the dual? There's a dual variable for every node in this graph. So it's maximum summation I pi bi subject to how will the dual constraints look like between node I and node j. So I've got a dual variable for pi. For every node, there's a dual variable. Okay. The edge xij, which connects I and j, xij shows up in the outgoing node for node I, the flow conservation for node I, and the flow conservation for node j. It will show up with a positive sign for for node I, and it will show up with a negative sign for node j. So it will be pi minus pj Cij, because this is a maximum minimization greater than equal to 0, maximization will be less than equal to. This is the dual for the network minimum cost network flow problem. The key in this is there are exactly two variables in every constraint in this which corresponds to the link. Okay. Okay. Is that clear? The dual formulation? Okay. So now let's look at network simplex. So I'm not going to show we're not going to do the full algorithm. I just want to give you the key ideas. So network simplex. So one, start with a feasible tree. Okay. Again, remember when we did this for LPs, we basically used the phase one LP. We solved the LP itself. You can do something similar here. Okay. Start with a feasible tree. Two, you can do this. So you're going to find the flow variables. Okay. One way you can do this is, remember, essentially you can xij. Okay. You can also do this by actually solving just the dual variables here. Xij is 1. So when a flow is 1, or sorry, when a flow is positive, this constraint will be tight, complementary slackness. Okay. So actually for network simplex, you can simply solve. So remember, every edge on a tree is part of my the flow. I'm hoping it to be positive on that link, right? So I'm going to solve. So I should expect this to be tight. So solve Pi minus Pj equal to Cij for every edge in the tree. Okay. And because we are going to drop one flow conservation constraint, you can basically set one of these dual variables. I mean, if you look at this, you can set one of the dual variables to be 0. So you basically solve just the set of linear equations. Okay. Okay. Next, you compute reduce costs. What is reduced cost? Cij minus Cb transpose B inverse Aj, but that is basically the dual variable times Aj. The dual variables are given here. So just minus essentially, and any column as 1 and minus 1, so it will be minus Pi minus Pj basically. Okay. You do this for every edge not in the tree. If everything is greater than or equal to 0, you're optimal. If not, you know which, if not, let Ij enter basis similar to simplex. What will happen is you have got a tree. So let's say you've got a tree. Let's say the reduced cost for this variable was negative, negative. That means you want to bring it into the basis. If you want to let it enter the basis, you have got a tree, you bring in a new edge, you get a cycle. Because if you have a tree and you have one extra edge, you're going to form a cycle. So the moment you bring an edge into a variable, into a tree, you'll get a cycle. Okay. You create a cycle. Okay. So the idea now is you try to send flow along the cycle. Okay. So you create a cycle. So let me go to next slide. Okay. So if all edges are in the same direction in the cycle, for example, I've got this. Okay. And let's say, for example, okay, not in this example, but let's say I have a graph which look like this. Maybe I brought in this. Maybe I've got an edge here. So maybe so let's say I've got a graph like this. Okay. This is my tree. And and let's say I've got an edge which shows up in this direction. Okay. I bring this into my basis. I form a cycle. This is a directed cycle. So what will happen is everything is moving in the same direction. If all edges in the same direction, essentially you send infinite flow along this cycle, and you have an unbounded optimal. Okay. So like we have in LPs, essentially if you have so in this case, you will have a cycle which everything is pointing in the same direction. So you try to increase flow, increase here, increase here, increase here. Everything moves in the same direction. So you can let things go off to infinity. You try to increase here, but you can increase flow here too and increase flow here too. Okay. If not, okay. So for example, in the graph we just saw, maybe it's like this. You're trying to increase flow here. If you're trying to increase flow here, there's a backward arc. So if you try to increase flow, as you send flow here, this flow will decrease and ultimately it'll become zero. So this will leave the basis. So if not, find backward arc where flow goes to zero. So this will enter the basis and this will leave the basis. So you'll have a spanning tree which now looks like this. Okay. And move to a new tree solution. Okay. So essentially, everything that you do for LPs, you can work through in the network case. Okay. I won't do a concrete example here, but hopefully the idea is clear. You can implement this. The book has an implementation if you want. You can look through it, but hopefully the idea is clear. Okay. I went through this a little bit quickly, but I just wanted you to see that everything has a parallel, essentially. Okay. Is there any question here? Okay. Okay. Fine. So, okay. So I want to mention one important thing here next, which is the idea of total unimodularity. Okay. This will also help us later on in discrete optimization. Okay. Which is a property of network flow problems. Okay. So what is total unimodularity? So a matrix A, so it's a property of a matrix. Okay. So matrix A is totally unimodular if the determinant, sorry, if the determinant of any square matrix, of any square submatrix of A is either 0, +1, or -1. So I give you a matrix A and I take any square submatrix in this. So I take a set of rows and a set of columns and I look at the determinant of this. That has to have a determinant which is 1, -1, or 0. That's a definition of a totally unimodular matrix. Okay. Okay. So it turns out that is the definition clear? Okay. So here's the theorem. The node arc incidence matrix is TU. Okay. So remember what a node arc incidence matrix is. It's this matrix, right? It's this matrix. Okay. The claim is that any submatrix, square submatrix, will have a determinant of either 0, -1, or +1 for this matrix. Okay. So why is this the case? Okay. Okay. So proof by induction. This is important because this will tell you that the solution will be integral. Okay. So for n equal to 1, okay, it's obvious. Okay, n equal to 1 is a single node. Okay. Okay. So it's just a single node. Okay, there's no edge basically. Okay. For n equal to 2, essentially you have an edge. So what is n equal to 2? N equal to 2 is if you have two nodes, that'll be 1 and -1. Determinant is either 1 or -1. So sort of obvious. Okay. Okay. Now let's consider. So suppose true for all square submatrices of size n-1 into n-1. Okay. So suppose actually maybe k-1 by. Okay. So I've got a matrix. Okay. Actually, let's maybe do this in slightly differently. Okay. Let me make this, be very careful with this. Okay. So by induction, so I've got a matrix A. Okay. It's of size n by m. Okay. Okay. Take square submatrix of size 1 by 1. Okay. What are the entries for this matrix? It's either a 1, minus 1, it's a 1 or a 0. These are only entries in this matrix, right? So every square submatrix of size 1 by 1 has an entry minus 1, 0 or 1. The determinant has to be, determinant of a single entry is just the entry itself. Okay. So it's true for k equal to 1. So let's assume it's true for all square submatrices of size k minus 1 by k minus 1. Now you assume, now take a matrix of size k by k, a square submatrix of size k by k. So let AK be a square submatrix of A of size k by k. What do we know about this matrix? What are the possibilities in this matrix? Okay. So three cases possible, three possibilities. One, this matrix AK, so this matrix AK might have a column of all zeros. So remember, every column has a 1, a minus 1, and a 1, 1, 1 plus 1, 1 minus 1, and all zeros. Okay. So it might have a column with all zeros. I'm taking a submatrix. AK. So one possibility is a column with all zeros. What is the determinant of this matrix? 0. Okay. So determinant of this AK has to be 0. Okay. So it satisfies the TU property. Determinant has to be 0, plus 1 or minus 1. Second possibility, AK has a column with exactly 1 plus 1 or minus 1, right? So you might have a column where there's exactly 1, 1, everything else is 0. Now, if you compute the determinant of this and if you use that cofactor formula, what will you do? You will take this 1 and compute the determinant of this submatrix of size k minus 1 by 1 plus 0 times the remaining plus 0. So you'll be left with the determinant of AK will be basically what? Plus or minus 1 times the determinant of a smaller k minus 1 by k minus 1 matrix. But this is already assumed by induction to be in 0 plus or minus 1. So this number has to be 0 or plus or minus 1, right? I'm multiplying either 0 plus or minus 1 with plus or minus 1. Okay. Last possibility, every column has 1 plus 1 and 1 minus 1. This is the last possibility in the matrix. So there's 1 plus 1, 1 minus 1. It should be rectangular. So let's say 0 should be square, right? It's a submatrix, square submatrix. If it has got every column has plus and 1 minus 1s, that's linearly dependent. Determinant of AK has to be 0. So basically, there are three possibilities, all of which imply it's totally unimodular. So basically, this means that this matrix is totally unimodular. So that means the determinant is either 0 plus or minus 1 for any submatrix. Now, what does this mean? This means that if you go back and think about our, like, you think about solving Bx equal to B. Okay, so theorem, and this is critical. Okay. Suppose I give you given an uncapacitated minimum cost network flow problem. Okay. And let's say it's got a finite optimal cost. Okay. So I'm not looking at the unbounded case. Okay. One, for every basis matrix, B inverse as integer entries. Two, if BI are integral, optimal flows are integral. Okay. And you can do something similar for the dual. Okay. So why is this the case? Why? Okay. So for an uncapacitated network flow problem, we just saw that A is TU, right? The A matrix is totally unimodular, which means the determinant of any matrix B has, if it's a basis matrix, determinant cannot be zero. So it has to be either B plus or minus one. This B inverse, the formula for a matrix inverse from Cramer's rule, B inverse is given by 1 by determinant of B with all these cofactors. Okay. These cofactors are basically just determinants of matrices themselves, basically. So everything here, this B inverse has got essentially integer entries, basically. Okay. So this B inverse from Cramer's rule will have integer entries, basically, because determinant is zero. So B inverse has integer entries from Cramer's rule. Okay. There's 1 by the determinant time all these cofactors, but each of those cofactors are integer entries, basically. Okay. And then what is the flow? My flow variables is B inverse B. If this is integer, and if this is integer, this has to be integer. Okay. So network flows has this very nice structure that if the problem has got integer entries, the flow values will be integer. So for example, when I do like a shortest path type problem, right? We didn't force integrality when we did the shortest path. Remember the shortest path problem I told you we discussed last class? I said we will just solve a linear programming problem. We'll find the shortest path by solving an LP. But what theory tells us is because of the network structure, our optimal solution will be integral because of this totally unimodular property. Okay, and this is very relevant because you can get an integral solution without even solving the integer program. Okay. Okay. Uh, okay. Any questions with this? So total unimodularity is an important property. By the way, just to make a point here, like every matrix with no, note, just if a matrix has, so here's an example of a matrix where the entries are only 1 and minus 1, but this is not TU. What's the determinant of this matrix? 1 into 1 minus minus 1 into 1. So determinant is 2. So if you essentially if you invert this matrix, you will get some fractional entries basically. Okay. So just a matrix having plus ones and minus ones and zeros is not enough for it to be TU. Okay. It requires the property is much stronger. You require a lot more in the matrix structure. Okay. So if it's a flow, if it's a network flow, if it's a like comes from the flow conservation constraints, it has a TU property. There are some other matrices which have this property. But for now, let's just focus on this. Okay. 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 So I want to now maybe talk about max flow min cut. Okay. Which let's see how far we get there. If we take 5 extra minutes, is it okay? Great. You guys have the energy for if you go 5 minutes past the class, or if it's too much, I can do it next class too. Is it too much overload material, or is it okay for you guys? You okay? Okay. Okay. Let me see if I can do max flow min cut in about 20 minutes. We'll see how far we can get. Okay. So okay. So we know what the max flow problem is. Okay. So max flow is this problem where we maximize the flow from node S to node T. Okay. So we have this node S, this node T. you're trying to maximize flow, and you have capacities on edges uij. Okay, and there's a graph and so on. Okay, so we have this flow conservation. Okay, this summation xij, again j ij in e minus the inflow, which is either v if you have a source node, minus v if it's a sink node, zero otherwise, and xij is between 0 and uij. Okay, so this is max flow. So one very important property in max flow is there's a natural representation of the dual formulation, which is called min cut. So LP duality in this network context gives you a corresponding formula of what's called a min cut problem. Okay, so I want to first write down the dual, and I want to try to interpret this dual as a min cut problem, and I want to show you how duality can be useful in these network flow problems too. Okay, so what's the dual? The dual of this problem will be there'll be a dual variable for each node, for each edge here, for each node here. So minimum, okay, and there'll be a dual variable in the max flow problem. There'll be a dual variable for these constraints. Okay, so there'll be a dual variable for the upper bound zij, and let's call this yi for these dual variables. Okay, so minimum zij times uij for every edge in this graph, subject to xijs are involved in the flow conservation for I, flow conservation for j, and the upper bound constraint. So you'll get a constraint like of the form yi minus yj plus zij. Compare that to the flow which is u, the xij has a objective of 0, 0, minimization. So this for every ij in E, where for this only for the source and the sink node, ys minus, sorry, it'll be y, if you take the v this side, it'll be yt minus ys equal to 1, where you require all these zijs to be non-negative. Okay. So this is the dual of this max flow problem. Okay, it's just writing a dual. Okay, a dual variable for every node conservation, a dual variable for every upper bound constraint. Just write down the dual, you will get this form. The question is, what does this dual actually mean? What is the corresponding interpretation of this in the network flow context? Okay. Okay. So what we will see next is this dual can be shown to be exactly a minimum FT cut. Okay. Problem. Because I have to define what a FT cut is. I will disturb that next. Okay. So I want to interpret the dual and talk about this max flow min cut duality. This is one of the important results in network flows. Okay. So let's do that next. Okay. So to first define what a ST cut is, what is a min cut problem? Okay. Okay. So what's an ST cut? Okay. So given ST cut is a subset of the nodes where S contains this node set S contains the link S. So this node set S contains this small node small s, and S bar, which is, let's say, V not containing S, contains this node T. Okay, where a capacity of the FT cut is the sum of all the capacities I in S, J in S bar, where Ij lies in the set H set. Okay. Okay. So let's do an example. It will be clear with an example. So let's say I've got this problem. Let's say this is S. Let's say this is node S. This is node T. Uh, uh, and let's keep things simple here. There's a let's say the capacity of 3 here. Um, we saw this last class, I think 3, 2, 1, 1, 3. Okay. Okay. So what's an ST cut? It's a cut of the graph, basically a cut through the graph, which splits the nodes into two sets. Small s should be on one side, small t should be on the other side. So for example, if I cut the graph this way, this node set will be just 1. S bar will be 2, 3, 4. Capacity is what? Of this cut is 3 plus 2. Edges going from I to j, where I is on this side and j is on this side. Capacity is 5. Here's another cut. Let's take this cut. This is a cut. This cut as node set is 1 and 2. In S, S bar is 3 and 4. Capacity is 2. 2 going this way, 1 going this way, 1 going this way. So 2 plus 1 plus 2 plus 1, 3 plus 1, 4. Yes? Question is, take every cut in this graph, every ST cut in the graph. Find me the minimum ST cut. Okay, this is obviously it looks like a complicated problem at start. Why? Because you have to take every subset of nodes which contains S and it does not contain T. But there are, like if there are 100 nodes, there'll be roughly of the order of 2 to the power 100 possibilities, right? You can take every combination of nodes which contains it. Okay. So it turns out this is actually not the way you should solve this problem. ST cut actually is an easy problem. Okay. And we'll see that next because it's just going to be the dual formulation is going to be the ST cut problem. Is the ST cut problem clear? So minimum ST cut is simply find ST cut of smallest capacity. Okay. Okay, so we are going to first interpret the dual and then I'll try to prove it formally. Okay, let's see how far we can go. Okay, let me see how much of the proof I can do. Okay, so first let's just interpret. Okay, just intuitively. Okay, okay, so what? Okay, I claim that every ST cut will be a feasible solution for this problem. Will give me a feasible solution. Of course, I have to define an ST cut. Okay, so what's an ST cut? So what's an ST cut? There is a node set S. There's a node set S bar. Small s is here. Small t is here. Okay. I'm going to define yi to be 0 for every I in S bar. And I'm going to define yi to be 1. I'm going to define yi to be, I guess, 1 for every node in S bar and 0 for every node in S. Okay. Okay. So what does this mean? Yt minus ys is equal to 1. It satisfies this constraint. Okay. So clearly yt minus ys is 1. That's fine. There's no other constraints on y except for the zij's. Okay. And there's no sign restrictions on y. So I have to define zij. So how do I define zij? So let this be in the following form. Let zij be 1 if I is in S and j is in S bar and 0 otherwise. Okay. So firstly, clearly Zij as definition is 0 or 1. It is non-negative. So it's definitely a feasible solution for that constraint. Okay. So I'd only worry about these constraints, yi minus yj plus zij. Okay. Let's look at this constraint, yi minus yj plus Zij non-negative. Okay. What can happen? So there's S, there is S bar. I can be here and J can be here. And I've got a link going from I to J. So for this link, what happens? By definition, Yi is 0, Yj is 1. 0, 1. Zij I've defined to be 1 if I go from I to j. So it's 0 minus 1 plus 1, that is 0. So it is feasible for this constraint when the edge goes from I to j, where it's a cut, part of the cut. Suppose you have a j here. Take an edge between two nodes in the same set. So this is for ij in the cut. Suppose it's it's in the same cut, it will be what? 0 minus 0 plus 0 if it is not in the cut. This is also clearly non-negative. I mean, it's clearly non-zero. The same thing will happen on this side. It will be 1 minus 1 plus 0, which is clearly non-zero, which is clearly equal to, I mean, it's basically non-negative. Okay. The last thing which could happen is I could have edges going across from S bar to S. Okay. If I've got an edge going this direction, what will happen there? Yi. So if I, let's say, is in S bar and J is in S. So in this example, I is in S, J is in S bar. In this, I and J both are in S. In this, both I and J are in S bar. The last case is if I is in S bar and J is in S. Okay. If this happens, what will happen? Yi will be 1. If I is in S bar, so for this case, Yi will be 1. Yj will be 0. And Zij will be 0. This is also, I mean, this is clearly non-negative. So every ST cut, if I code it as a binary, using binary variables, is a feasible solution for this problem. If Zij is 1, it's part of the cut, I pick up the capacity Uij. So the optimal value of this LP, so what does this mean? Optimal value of the dual has to be lesser than or equal to the minimum FT cut. This has to be the case, right? Because I've given you a set of dual feasible solutions, each of which is feasible. Every ST cut is feasible for this problem if I code it in this way, and the corresponding cut capacity comes up in my objective. I could take all the cuts, each of them gives me a dual feasible solution. I could pick the smallest among them. That will be a solution to this problem. It may not be optimal, but it's a solution for this problem. So I know definitely the optimal value of this is below the minimum ST cut value. The point is, in fact, they are equal. Okay. Was this clear, this part of the argument, what we did so far? Why optimal value of dual is below the minimum ST cut? Yes? Okay. Yes or no? If I'm going too fast, please tell me. Yeah. I can slow down. Okay. Okay. So first claim, max flow, which is the primal, is less than min cut. Okay. So this is exactly weak duality for LPs. Okay. Why is this the case? Okay. Okay. You take S bar, where small node S is here and capital node T is here. Okay. You got incoming flow V, outgoing flow V. You got flow conservation. Okay. Okay. So take any feasible flow. In the network. Okay. So what does it mean, feasible flow? You take any feasible solution to the primal. Okay. So take any Xij which satisfy these constraints. Okay. I will add up the flow conservation for every node which is in the set S, basically. Okay. So, okay. Sum up uh, the flow conservation constraints for all nodes I in S, okay, where S bar is a ST cut. Okay. So I partition my nodes into two parts, S and S bar. I take the flow conservation constraints for only the nodes in S, capital S, and I add up. Okay. So I've got incoming flow V. I add up flow conservation. So there might be a flow going from here to this node. It's positive, negative, cancels out each other. Okay. Maybe there are flows coming here, positive, negative, cancels out each other. There are that could be flows going from S to S bar. Flow conservation will say pick up this for this node, but I don't take the flow conservation for this node. I'm only taking flow conservation on this part. So all these links will show up only one time. So I will get summation xij for every I in S, j in S bar, ij in E, and then I might have edges which go from S bar to S. This will show up in flow conservation for these nodes only one time, but with a minus one. Okay. So you'll have the total flow will be minus summation xj ji. J is in S, I is in S bar, ji in E. Okay. So if you add up flow conservation, you will get basically V equal to total flow going out from S to S bar minus total flow coming in from S bar to S. Just add up these constraints. Okay. Okay. But this gives me an upper bound. Why? Because this thing is bounded from each of these terms is bounded from above by uij. Each of these terms is bounded from below by 0. If I want an upper bound on this total sum, I will take an upper bound on the positive parts and take a lower bound on the negative parts. So this will be less than equal to uij, I in S, j in S bar, ij in E. This is exactly a cut capacity. Flow is less than equal to cut capacity. I can pick the smallest cut. It will be an upper bound. I can maximize flows. It will be an upper bound. So this is LP weak duality. Okay. Is that clear? Okay. Now what we have to show is strong duality. Okay. Now we can stop here and I can do it next class. Maybe it'll give you time to internalize and we can do it next class, or it'll take me about 10 more minutes. I'll leave it to you guys. If you want to internalize, we can do it next time, or we can take 10 more minutes and finish it off. You tell me. I'll leave it to you guys. Huh? You need time to internalize? Okay, then we can do it next time. So basically what we'll do next time is we'll show max flow is equal to min cut. I will complete that. And then we will start on, I'll tell you a bit about, so just to tell you where we are going, next week I will try to, so I'll finish up this and I will just try to introduce to you ellipsoid and interior point methods. We won't do it in as much detail as simplex, but I want to just tell you a couple of other methods for solving LPs. That will be week 9. And then from week 10 till about week 13, we will do only discrete optimization. So we'll do integer programming, and we will sort of continue. We'll look at ideas and IPs basically. Okay. Okay. Let's stop here. I will complete this on next Wednesday. Okay. Fine. Thank you. Have a good day. Yes.